A lithium polymer battery, or more correctly lithium-ion polymer battery, is a rechargeable battery of lithium-ion technology in a pouch format. Unlike cylindrical and prismatic cells, LiPos come in a soft package or pouch, which makes them lighter but also less rigid. The designation, lithium polymer, has caused confusion among battery users because it can be interpreted in two ways. Originally, lithium polymer represented a developing technology using a polymer electrolyte instead of the more common liquid electrolyte. The result is a plastic cell, which theoretically could be thin, flexible, and manufactured in different shapes, without risk of electrolyte leakage. These batteries are available although the technology has not been fully developed and commercialized, and research is ongoing. The second meaning appeared after some manufacturers applied the polymer designation to lithium-ion cells contained in a non-rigid pouch format. This is currently the most popular use, in which polymer refers more to a polymer casing, rather than a polymer electrolyte. While the design is usually flat and lightweight, it is not truly a polymer cell, since the electrolyte is still in liquid form, although it may be plasticized or gelled through a polymer additive. These cells are sometimes designated as LiPo. However, from a technological point of view, they are the same as the ones marketed simply as Li-ion, since the underlying electrochemistry is the same. This article concerns the second, more extended meaning, while the first meaning is discussed only in the last section. The name lithium polymer is widespread among users of radio-controlled models, for which it may indicate a single cell or a battery pack with cells connected in series or parallel. The more general term, lithium-ion, is used almost everywhere else, including consumer electronics such as mobile phones and notebook computers, and battery-powered electric vehicles. History. LiPo cells follow the history of lithium-ion and lithium metal cells, which underwent significant research during the 1980s. Reaching a significant milestone with Sony's first commercial cylindrical Li-ion cell in 1991. After that, other packaging techniques evolved, including the pouch format, now also called LiPo. Design, origin and terminology. The original kind of cell, named lithium polymer, has technologically evolved from lithium-ion and lithium metal batteries. The primary difference is that instead of using a lithium salt electrolyte held in an organic solvent, the battery uses a solid polymer electrolyte such as poly, or poly. The solid electrolyte can be typically classified as one of three types: dry SPE, gelled SPE and porous SPE. The dry SPE was the first used in prototype batteries, around 1978 by Michel Armand, Domaine University, and 1985 by ANVAR and Elphie Aquitaine of France, and Hydro-Quebec of Canada. From 1990 several organizations like Mead and Valence in the United States and GSU ASA in Japan developed batteries using gelled SPs. In 1996, Belcore in the United States announced a rechargeable lithium polymer cell using porous SPE, but without success in commercialization. In parallel to the development of these polymer electrolyte batteries, the term lithium polymer started being used for liquid electrolyte Li-ion cells in pouch format. These cells started appearing in consumer electronics around 1995, eventually becoming known as LiPo for some applications. The confusion in the names may stem from the construction of the basic lithium-ion cell. A typical cell has four main components: positive electrode, negative electrode, separator and electrolyte. The separator itself may be a polymer, such as a microporous film of polyethylene or polypropylene. Thus, even when the cell has a liquid electrolyte, it will still contain a polymer component. In addition to this, the positive electrode can be further decomposed in three parts: the lithium transition metal oxide, a conductive additive, and a polymer binder of poly. The negative electrode material may have the same 3 parts, only with carbon replacing the lithium metal oxide. Therefore, even if a bare, unfinished cell lacks a polymer separator, or any liquid or solid electrolyte, it may still have a polymer component in the active materials of the electrodes. This polymer, however, is just a small fraction, typically less than 5% by weight, and does not participate in the electrochemical reactions, being only useful for binding the active particles together to maintain good conductivity, and help make the slurry mix adhere well to the copper and aluminium foils that compose the current collectors of the battery cell. Working principle. Just as with other lithium-ion cells, LiPos work on the principle of intercalation and intercalation of lithium ions from a positive electrode material and a negative electrode material, with the liquid electrolyte providing a conductive medium to prevent the electrodes from touching each other directly. A microporous separator is in between, which allows only the ions and not the electrode particles to migrate from one side to the other. Charging. Just as with other kinds of lithium-ion cells, the voltage of a LiPo cell depends on its chemistry and varies from about 2.7–3.0 V to about 4.20–4.35 V for cells based on lithium metal oxides, and around 1.8–2.0 V to 3.6–3.8 V for those based on lithium iron phosphate. The exact voltage ratings should be specified in product data sheets, with the understanding that the cells should be protected by an electronic circuit that won't allow them to overcharge nor over-discharge under use. For LiPo battery packs with cells connected in series, a specialized charger may monitor the charge on a per-cell basis so that all cells are brought to the same state of charge, applying pressure on LiPo cells. Unlike lithium-ion cylindrical and prismatic cells, which have a rigid metal case, LiPo cells have a flexible, foil-type case, so they are relatively unconstrained. By themselves, the cells are over 20% lighter than equivalent cylindrical cells of the same capacity. Being lightweight is an advantage where the application requires minimum weight, such as in the case of radio-controlled models. However, it has been investigated that moderate pressure on the stack of layers that compose the cell results in increased capacity retention, because the contact between the components is maximized and delamination and deformation is prevented, which is associated with increase of cell impedance and degradation. Applications. LiPo cells provide manufacturers with compelling advantages. They can easily produce batteries of almost any desired shape. For example, the space and weight requirements of mobile phones and notebook computers can be completely satisfied. Also, they have low self-discharge rate, which is about 1%. Radio-controlled equipment and airsoft LiPo batteries have just about taken over in the world of radio-controlled aircraft, radio-controlled cars and large-scale model trains, where the advantages of lower weight and increased capacity and power delivery justify the price. As of the beginning of 2013, LiPo packs of 1.3 R exist, providing 45 C continuous discharge, and short-time 90 C bursts. Bigger packs of 4.5 R may feature discharge rates of 70 C, with 140 C bursts. LiPo packs also see widespread use in airsoft, where their higher discharge currents and better energy density compared to more traditional NIMH batteries has very noticeable performance gain. The high discharge currents do damage the switch contacts due to arcing, so it is advised to either use a solid-state MOSFET switch or clean the trigger contacts regularly. Personal electronics. LiPo batteries are pervasive in mobile phones, tablet computers, power banks, very thin laptop computers, portable media players, wireless controllers for video game consoles, electronic cigarettes, and other applications where small form factors are sought and the high energy density outweighs cost considerations. electric vehicles. Lithium-ion cells in pouch format are being investigated to power battery electric vehicles. While it is possible to use a large number of cells of small capacity to obtain required levels of power and energy to drive a vehicle, some manufacturers and research centers are looking into large format lithium-ion cells of capacities exceeding 50 Ah for this purpose, with higher energy content per cell. The number of cells and electrical connections in a battery pack would certainly decrease, but the danger associated with individual cells of such high capacity might be greater. Hyundai Motor Company uses this type of battery in some of their hybrid vehicles, as well as Kia Motors in their battery electric Kia Soul. The Polymer blue car, which is used in car-sharing schemes in several cities, also uses this type of battery. Light aircraft and self-launching gliders are being produced, such as the Elisport Silent 2 Electro and the Pipistrel Watsip. Some larger gliders, such as Scheme Perth Ventus 2, use the technology for self-sustaining motor safety. LiPo cells are affected by the same problems as other lithium-ion cells. This means that overcharge, overdischarge, overtemperature, short-circuit, crush and nail penetration may all result in a catastrophic failure, including the pouch rupturing, the electrolyte leaking, and fire. All Li-ion cells expand at high levels of state of charge or overcharge, due to slight vaporization of the electrolyte. This may result in delamination, and thus bad contact of the internal layers of the cell, which in turn brings diminished reliability and overall cycle life of the cell. This is very noticeable for LiPos, which can visibly inflate due to lack of a hard case to contain their expansion. Compared to cylindrical Li-ion cells, LiPos lack integrated safety devices such as a current-interrupting device or a positive temperature coefficient material that is able to protect against an overcurrent or an overtemperature. Lithium cells with true polymer electrolyte. Although the name lithium polymer is mostly applied to lithium-ion cells in pouch format, which still contain a liquid electrolyte, there are electrochemical cells with actual polymer electrolytes, which however have not reached full commercialization and are still a topic of research. Prototype cells of this type could be considered to be between a traditional lithium-ion battery and a completely plastic, solid-state lithium-ion battery. The simplest approach is to use a polymer matrix, such as polyvinylide and a fluoride or poly, gelled with conventional salts and solvents, such as LiPo6 in EC, DMC, DEC. Nishi mentions that Sony started research on lithium-ion cells with gelled polymer electrolytes in 1988, before the commercialization of the liquid electrolyte lithium-ion cell in 1991. At that time, polymer batteries were promising and it seemed polymer electrolytes would become indispensable. Eventually, this type of cell went into the market in 1998. However, Skrosati argues that, in the strictest sense, gelled membranes cannot be classified as true polymer electrolytes, but rather as hybrid systems where the liquid phases are contained within the polymer matrix. Although these polymer electrolytes may be dry to the touch, they can still contain 30% to 50% liquid solvent. In this regard, an open question remains on how to really define what a polymer battery is. Other terms used in the literature for this system include hybrid polymer electrolyte, where hybrid denotes the combination of the polymer matrix, the liquid solvent and the salt. It was a system like this that Belcore used to develop an early lithium polymer cell in 1996, which was called plastic lithium-ion cell, and subsequently commercialized in 1999. A solid polymer electrolyte may be, for example, a compound of lithium bisamide and high molecular weight poly, or a high molecular weight poly. The performance of these proposed electrolytes is usually measured in a half-cell configuration against an electrode of metallic lithium, making the system a lithium metal cell, but it has also been tested with a common lithium-ion cathode material such as lithium iron phosphate. Other attempts to design a polymer electrolyte cell include the use of inorganic ionic liquids such as 1-butyl-3-methylimidazolium tetrafluoroborate as a plasticizer in a microporous polymer matrix like poly.